static electricity can present a significant fire hazard, especially when handling flammable liquids. Proper grounding is critical to dissipate static charges and prevent ignition. The National Electrical Code (NEC) requires that equipment be grounded to prevent electrical shock and fire hazards. However, there are no specific requirements for static grounding. Some best practices for static grounding include using a separate grounding system. A dedicated static grounding system is recommended to avoid interference with the electrical grounding system. It's also important to provide a low resistance path to ground. The grounding strap should have a low electrical resistance to ensure effective charge dissipation. Bond all conductive surfaces so that all conductive surfaces, including the skid, panel, and pegs, should be bonded together and grounded to the static grounding system. In the scenario you described, with the ground conductor connected to the panel and all bonded surfaces, it meets the best practices for static grounding. If there is a request for an additional static ground, it is generally not redundant as long as it is connected to a separate grounding system. However, it is important to ensure that there is no electrical connection between the static grounding system and the electrical grounding system. Based on the information provided, the grounding system implemented is sufficient for both static and electrical grounding. An additional static ground is not strictly necessary, but could provide added peace of mind. It is important to ensure that both the static and electrical grounding systems are properly installed and maintained to minimize the risk of fire and electrical hazards. The core concept here is understanding how to safely dissipate static electricity, particularly when dealing with flammable materials. Grounding provides a path for static charges to flow harmlessly to the earth, preventing them from building up and potentially causing a spark. The NEC focuses primarily on electrical safety related to power systems, not specifically static electricity. Therefore, while the NEC provides guidelines for grounding electrical equipment, it doesn't offer detailed instructions for static grounding. The key to effective static grounding is ensuring a low resistance path. Resistance hinders the flow of electrical charge. A low resistance grounding strap allows static charges to dissipate quickly and efficiently. Bonding is another critical aspect. By bonding all conductive surfaces together, you ensure that they are at the same electrical potential. This prevents static charges from accumulating between different objects and creating a spark. Using a separate grounding system for static control can be advantageous. It minimizes the risk of interference with the electrical grounding system, which is primarily designed to protect against electrical faults and shocks. A dedicated static grounding system provides a more controlled and reliable path for static charge dissipation. When considering an additional static ground, it's crucial to maintain separation between the static and electrical grounding systems. Connecting them together could create a path for electrical faults to flow through the static grounding system, potentially compromising its effectiveness and creating safety hazards. Ultimately, the goal is to create a safe working environment where the risk of static electricity-induced fires or explosions is minimized. Proper grounding and bonding practices are essential for achieving this goal. There are several factors to consider when designing and implementing a static grounding system. Firstly, the materials used for grounding straps and connections should be highly conductive, such as copper or aluminum. Secondly, the size of the grounding conductors should be adequate to handle the potential static charge buildup. Thirdly, the grounding connections should be clean, secure, and free from corrosion to ensure a low resistance path. The frequency of inspections and maintenance of the grounding system is crucial. Grounding connections can loosen or corrode over time, increasing resistance and reducing effectiveness. Regular inspections can identify and address these issues before they compromise the safety of the system. Consider the environment in which the grounding system is installed. In corrosive environments, special precautions may be necessary to protect grounding connections from degradation. This might involve using corrosion-resistant materials or applying protective coatings. The importance of training personnel on proper static grounding procedures cannot be overstated. Employees who handle flammable materials should be aware of the risks of static electricity and how to properly use grounding equipment. Regular training sessions can help reinforce these concepts and ensure that everyone is following the correct procedures. Documentation of the grounding system is also important. Maintain records of grounding system design, installation, inspection, and maintenance. This documentation can be valuable for troubleshooting problems and demonstrating compliance with safety regulations. In situations where flammable liquids are transferred between containers, such as with the peaks mentioned, it is essential to ground both containers before starting the transfer. This prevents static charges from building up on either container and creating a spark during the transfer process. Consider using static grounding clamps with visual indicators. These clamps provide a clear indication of whether a good grounding connection has been established. This can help prevent accidental disconnections and ensure that grounding is always in place when needed. Review and update the grounding system periodically. As processes change or new equipment is introduced, it may be necessary to modify the grounding system to ensure that it continues to provide adequate protection. Staying up to date with industry best practices and relevant safety standards is also important. When dealing with hazardous materials, it is always best to err on the side of caution. If there is any doubt about the effectiveness of the grounding system, consult with a qualified electrical engineer or safety professional. They can assess the situation and recommend appropriate solutions. Remember that static electricity can be generated by a variety of sources, including the movement of fluids, friction between surfaces, and even the movement of people. Therefore, it is important to consider all potential sources of static charge when designing a grounding system. In addition to grounding, other static control measures may be necessary in some situations. These measures include using static dissipative materials, controlling humidity, and using air ionizers. Static dissipative materials help to reduce the buildup of static charges on surfaces. Controlling humidity can also help, as high humidity levels make it easier for static charges to dissipate. Air ionizers generate ions that neutralize static charges in the air. A comprehensive static control program should include a combination of these measures tailored to the specific hazards and conditions of the workplace. The ultimate goal is to create a safe and productive work environment where the risk of static electricity-related incidents is minimized. By understanding the principles of static grounding and implementing appropriate control measures, you can significantly reduce the potential for fires, explosions, and other hazards. When evaluating the grounding system, consider the resistance to ground. Ideally, the resistance should be as low as possible, typically less than 1 ohm. A higher resistance indicates a problem with the grounding connection or the grounding conductor. Regular testing of the resistance to ground is essential to ensure that the grounding system is functioning properly. Use a calibrated ground resistance meter to perform these tests. The meter should be capable of measuring low resistances accurately. When performing ground resistance tests, it is important to disconnect the equipment from the power supply to avoid inaccurate readings. Follow the manufacturer's instructions for using the ground resistance meter. If the resistance to ground is higher than the recommended value, investigate the cause and take corrective action. This may involve tightening grounding connections, cleaning corroded surfaces, or replacing damaged grounding conductors. It's also crucial to ensure that the grounding electrode is properly installed and maintained. The grounding electrode is the point where the grounding system connects to the earth. It should be buried deep enough to ensure good contact with the soil. The type of grounding electrode used will depend on the soil conditions. Common types of grounding electrodes include ground rods, ground plates, and underground metallic water pipes. Regularly inspect the grounding electrode for corrosion or damage. If the electrode is corroded or damaged, it should be replaced. In areas with poor soil conductivity, it may be necessary to use multiple grounding electrodes connected in parallel to achieve a low resistance to ground. When installing multiple grounding electrodes, space them at least twice the length of the electrode apart to avoid reducing their effectiveness. Consider using a ground-enhancing compound to improve the conductivity of the soil around the grounding electrode. These compounds can help to reduce the resistance to ground, especially in areas with dry or sandy soil. When working on electrical equipment, always verify that the equipment is properly grounded before starting any work. Use a multimeter to check the continuity between the equipment grounding conductor and a known ground point. If there is no continuity, do not proceed with the work until the grounding issue is resolved. In addition to grounding, equipotential bonding is another important safety measure. Equipotential bonding involves connecting all conductive surfaces in an area together to create a common electrical potential. This helps to prevent voltage differences from developing between different surfaces, which could lead to electrical shock hazards. Equipotential bonding is particularly important in areas where there is a risk of electrical shock, such as bathrooms, swimming pools, and industrial facilities. When implementing equipotential bonding, use appropriately sized bonding conductors and ensure that all connections are secure and corrosion resistant. Regularly inspect the bonding connections to ensure that they are in good condition. Remember that grounding and bonding are essential components of a comprehensive electrical safety program. By understanding the principles of grounding and bonding and implementing appropriate measures, you can significantly reduce the risk of electrical shock, fire, and other hazards. Consulting with a qualified electrical engineer or safety professional is always recommended when designing or modifying an electrical system. They can provide expert guidance on grounding, bonding, and other safety-related issues. Staying up to date with the latest electrical codes and standards is also important. These codes and standards provide valuable information on how to design, install, and maintain safe electrical systems. Consider attending training courses or workshops on electrical safety. These courses can help you to develop the knowledge and skills necessary to work safely with electricity. Always follow safe work practices when working with electrical equipment. This includes wearing appropriate personal protective equipment, such as gloves and safety glasses, and energizing equipment before working on it. Be aware of the potential hazards of electricity and take steps to protect yourself and others. Electricity is a powerful force that can be dangerous if not handled properly. By following safe work practices and taking appropriate precautions, you can minimize the risk of electrical accidents.